Welcome back to DSA with Python. In this video, we are doing a comprehensive deep dive into system design, the art and science of building large-scale distributed systems. We will cover everything from the foundational building blocks, scaling, caching, databases, all the way up to real-world case studies like designing YouTube, a chat system, and a URL shortener. Whether you are preparing for a senior engineering interview or just want to understand how the systems you use every day actually work, this one is for you. Let's get into it. Next. So what exactly is system design? At its core, system design is the process of defining the architecture of a system, its components, modules, interfaces, and how data flows between them, all to satisfy a specific set of requirements. It is not about writing a single function or class. It is about deciding what boxes exist, what each box does, and how they talk to each other. There are two dimensions to system design. The first is high-level design, or HLD. This is the big picture. Which services exist, what the data stores look like, how traffic flows from the user, all the way to the database and back. The second is low-level design, or LLD. This is where you get into implementation details, the class diagrams, the database schemas, the specific algorithms. And why does this matter? Because every product you use, Twitter, Netflix, Uber, WhatsApp, is built on carefully designed systems. The choices made at the architecture level determine whether a product can handle 1,000 users or 100 million. They determine how much it costs to run, how quickly it recovers from failures, and how easily engineers can add new features. System design is also the core skill tested in senior and staff-level engineering interviews at every top tech company. If you have ever wondered what separates a senior engineer from a software engineer in an interview context, this is it. The diagram on the right shows the design cycle. You always start with requirements. Those requirements drive your high-level architecture, which then informs the low-level implementation. You observe the running system, learn from it, and requirements evolve. It is a continuous loop. Next, before you draw a single box or pick a single database, you need to thoroughly understand what you are building. This is requirements engineering, and it is arguably the most important step. The golden rule is, never assume. Always ask, always clarify. Requirements split into two categories. First, functional requirements. These describe what the system does. What are the core use cases? Users can upload files, users can send messages, the system processes payments, search returns results in under 200 milliseconds. These are the features. Then there are non-functional requirements. These describe how well the system does its job. They don't add features. They define quality. You want numbers here. Availability 99.99% uptime. Latency P99 under 100 milliseconds. Throughput 100,000 requests per second. Durability 0 data loss. Consistency eventual or strong. Scalability 10 times growth in 2 years. If you cannot quantify a non-functional requirement, you cannot verify whether your design meets it. Now, back of the envelope estimation. Before you design anything, you need rough numbers. How many requests per second? How much storage? How much bandwidth? Memorize these latency numbers. L1 cache, half a nanosecond. RAM, 100 nanoseconds. SSD random read, 100 microseconds. Same data center network round trip, half a millisecond. Cross data center, 50 milliseconds. HDD seek, 10 milliseconds. For storage. 1 character is 1 byte. AUUID is 16 bytes. A compressed image is about 300 kilobytes. 1 minute of HD video is roughly 100 megabytes. And the key formula for traffic estimation. Take your daily active users, multiply by the average number of requests per user per day, divide by 86,400 seconds, and that gives you your requests per second. Simple, powerful, and expected in every interview. Next. Once you understand your requirements, the first scalability question is, how do you handle more load? There are two fundamental approaches, scale up or scale out. Vertical scaling means adding more power to a single machine. Bigger CPU, more RAM, faster disks. It is simple. Your code does not need to change at all. The benefits are clear. No distributed systems complexity, transactions are easy, and your architecture stays simple. But the limitations are real. There is a hard ceiling. You can only buy the biggest server that exists. You still have a single point of failure. And at the high end, that monster server gets extremely expensive. Horizontal scaling means adding more machines and distributing load across them. This gives you near infinite capacity in theory. If one node fails, the others keep serving traffic, and you can use commodity hardware instead of specialty servers. The trade-off is complexity. You have to manage distributed state, coordinate consistency, and route traffic intelligently with a load balancer. The practical rule of thumb. Scale vertically first until it becomes painful, either in cost or in hitting the ceiling. Then scale horizontally. Most production systems at real scale use both strategies. vertical to get the most out of each individual node, and horizontal to add aggregate capacity. Next, once you have multiple servers, you need something in front of them to decide which server handles each incoming request. That is the load balancer. A load balancer distributes incoming requests across a pool of servers to maximize throughput, minimize latency, and eliminate single points of failure. Without it, horizontal scaling doesn't work. There are several load balancing algorithms. Round robin simply rotates through all servers in order. Request 1 to server 1, request 2 to server 2, and so on. It is simple and works well when all servers are equally powerful. Weighted round robin is the same idea but assigns more traffic to higher capacity servers. Least connections routes each new request to whichever server currently has the fewest active connections. Great for workloads with variable request durations. IP hash routes the same client IP to the same server every time. Useful for stateful applications where session stickiness is needed. And consistent hashing is the most sophisticated, minimal reshuffling, when nodes join or leave. We will come back to this concept in detail shortly. Load balancers also operate at different layers. Layer 4, the transport layer, routes by IP address and TCP port. It is extremely fast, but has no visibility into what is inside the request. Layer 7, the application layer, can inspect the actual HTTP content, the URL path, headers, cookies. This enables powerful things like routing all API calls to one group of servers, and all static assets to another. The diagram shows a production-grade setup, an active/standby load balancer pair, so the load balancer itself is not a single point of failure. The active one sends heartbeat signals to the standby. If the active fails, the standby takes over. Behind the load balancer sit your web servers, and they share a database and a cache layer. One more important concept, health checks. The load balancer continuously pings each server, typically at an HTTP endpoint like /health. If a server fails 3 consecutive checks, it is automatically removed from rotation. This is how the system self-heals without human intervention. If load balancing is about routing traffic, caching is about avoiding work. And in high-traffic systems, it is often the single biggest lever you have for performance. Caching stores copies of frequently accessed data in a fast access layer, usually in memory, like Redis, so that you do not have to go all the way to the database for every request. The insight behind caching comes from the Pareto principle. 80% of your reads are served by just 20% of your data. If you can keep that 20% in memory, you have dramatically reduced your database load. Eviction policies determine what gets removed when the cache is full. LRU, least recently used, removes the item that was accessed the longest time ago. It is the most common. LFU, least frequently used, removes the item that has been accessed the fewest times overall. FIFO simply removes the oldest item, regardless of access patterns. TTL sets an expiry time. The item is automatically removed after a fixed duration. Invalidation strategies determine when and how you update the cache when data changes. Write-through. You write to the cache and the database simultaneously on every write. Your cache is always consistent with your database, but every write has higher latency, because it must hit 2 systems. Write behind, also called write back. You write to the cache immediately and flush to the database, asynchronously in the background. Writes are very fast, but if the cache crashes before the flush, you lose data. Cache aside, the most common pattern. Your application code checks the cache first. On a miss, it loads from the database, and populates the cache. The cache is only populated on demand. The diagram shows cache aside in action. The client hits the application. The application checks Redis. On a hit, it returns immediately. On a miss, it queries the database, puts the result in the cache, and then returns. 3 cache failure modes every engineer should know. Cache stampede. Many requests arrive simultaneously for data that just expired or was evicted. They all miss the cache and hammer the database at once. The fix is mutex locks, or probabilistic early expiration. Cache penetration. Requests for keys that do not exist in the database at all. An attacker can use this to bypass your cache entirely. The fix is a Bloom filter to reject clearly non-existent keys before they hit the database. Cache avalanche. Many keys all expire at exactly the same time, perhaps because they were all loaded together with the same TTL. The fix is to add random jitter to TTL values so expirations are spread out. Now let us talk about databases, arguably the most consequential architectural decision you will make. Relational databases. The SQL families store structured data in fixed schema tables with rows and columns. They enforce data integrity through constraints, support complex join queries across multiple tables, and provide ACID transactions. Atomicity, consistency, isolation, and durability. Examples are PostgreSQL, MySQL, and SQLite. Choose SQL when you need financial-grade consistency, payments, orders, inventory. When your data is naturally relational, and you need to query across those relationships. When data integrity must be enforced at the database level, not the application level. Now, NoSQL is not a single thing. It is a family of different database types, each optimized for a different problem. Document databases like MongoDB store flexible JSON documents. No fixed schema. Each document can have different fields. Key value stores like Redis and DynamoDB are essentially hash maps, blazingly fast for simple lookups, sessions, and leaderboards. Wide column stores like Cassandra handle massive write throughput, great for time series data and IoT. Graph databases like Neo4j model entities and their relationships natively, perfect for social networks and recommendation engines. Click now the most important theoretical concept in distributed databases, the CAP theorem. A distributed system can only guarantee two of these three properties at the same time. Consistency. Every read returns the most recent write. Availability. Every request gets a response, even if it might be stale. Partition tolerance. The system keeps working even when network partitions split your nodes. Here is the key insight. Network partitions are inevitable in any real distributed system. You cannot avoid them. So you are always trading between C and A. Partition tolerance is mandatory. That means you choose. CP systems sacrifice availability to stay consistent. When there is a partition, they return an error rather than stale data. AP systems sacrifice consistency for availability. They return a response even if it might be slightly out of date. Next, once a single database cannot keep up, you have two main scaling strategies, replication and sharding. They solve different problems. Replication is primarily for read scalability and high availability. One primary node accepts all writes and replicates its data asynchronously to one or more replica nodes. Your application directs all writes to the primary and spreads reads across the replicas. Click the benefits. Read throughput scales linearly with the number of replicas. And if the primary fails, you can promote a replica. That is your failover strategy for high availability. The trade-offs. Replication lag. Because replication is asynchronous, replicas are slightly behind the primary, typically milliseconds to seconds. If a user writes data and immediately reads it from a replica, they might see stale results. And the primary is still the write bottleneck. All writes still go through one node. Click sharding solves the write bottleneck. Instead of one giant database, you horizontally partition your data across multiple database nodes called shards. Each shard independently owns a subset of the total data. Writes are distributed across all shards, not concentrated on one. The common sharding strategies. Range. Shard by a key range, like usernames A through M on shard 1, N through Z on shard 2. Hash. Compute hash key, %n to determine the shard. Directory. Maintain a lookup table that maps each key to its shard. Geo. Route by the user's geography. Click, and the problem sharding introduces. Hot shards. If your sharding key is not well chosen, one shard gets a disproportionate amount of traffic. Consistent hashing helps. Cross-shard joins. Joining data that lives on different shards requires expensive scatter-gather operations, or is impossible entirely. Design your schema to keep related data together. Resharding. When you need to add nodes to the cluster, you must migrate data between shards. Consistent hashing minimizes how much data moves. Next, speaking of consistent hashing, let us understand exactly why it matters, because it comes up constantly in system design discussions. Here's the problem with the naive approach. Shard equals hash, key, modulo n. When n changes, say you add a new server or remove a failed one, almost every single key remaps to a different shard. That means you have to migrate nearly all of your data at once. For a database with billions of records, that is catastrophic. Click consistent hashing elegantly solves this. The idea is elegant. Imagine a ring, a circular hash space from 0 to 2 to the 32nd power. You place both your server nodes and your data keys onto this ring, using a hash function. Each key belongs to the first node you encounter, traveling clockwise around the ring from the key's position. Look at the diagram. Key user _42 hashes to position 120, and it gets assigned to node A at position 150, the first node clockwise. When you add a new node, only the keys between the previous node's position and the new node's position need to be remapped. When you remove a node, only its keys move to the next clockwise node. All other keys are completely unaffected. Click the math works out beautifully. Instead of remapping nearly all k keys when n changes, you only remap k divided by n keys on average, a fraction of the total. Click virtual nodes take this further. Instead of each physical server appearing once on the ring, it appears multiple times, typically 150 or more virtual positions. This ensures the load is distributed evenly, even when servers have different capacities, and eliminates hotspots that can appear with sparse ring placement. Consistent hashing is the foundation of DynamoDB, Cassandra, Redis cluster, Memcached Katama algorithm, and Akamai's CDN infrastructure. It is a fundamental tool in distributed systems engineering. Next, so far we have talked about scaling compute and databases. But what about content? How do you serve images, videos, and static files to users spread across the globe with low latency? That is what a CDN does. A content delivery network is a geographically distributed network of edge servers, called points of presence, or POPs, that cache your content close to your end users. Instead of every user in Tokyo fetching an image from your server in Virginia at 150 milliseconds round trip, they fetch it from a CDN edge node in Tokyo at 5 milliseconds. Click CDN's cache static assets, images, CSS, JavaScript, fonts. They serve video and audio segments for streaming. Modern CDNs even cache pre-rendered HTML and short TTL API responses. Click 2 Operational Models. Push CDN. You proactively push content to CDN nodes before it is requested. Best for large, rarely updated files like software downloads. Pull CDN. The CDN fetches from your origin server on the first miss, then caches the result for subsequent requests. This is simpler to operate, and far more common. Click the diagram shows exactly how it works. A user in New York and a user in London both request the same asset. Each gets routed to their nearest CDN edge node. The first time each POP sees the request, it fetches from your origin server, just once. Every subsequent request is served locally, at millisecond latency, without ever touching your origin. Click You control CDN caching behavior with the cache control header on your origin responses. For example, cache control, public, max age equals 86,400, tells CDN nodes to cache this resource for 24 hours. The big players are Cloudflare, AWS CloudFront, Fastly, and Akamai. Next, now that we have covered the infrastructure layer, let us talk about communication, how services and clients actually talk to each other. There are 3 dominant patterns for API communication, and choosing the right one matters. REST, representational state transfer, is the classic model. It is stateless, HTTP-based, and uses standard verbs that map to CRUD operations. Get to read, post to create, put to replace, patch to partially update, delete to delete. Resources are identified by URLs. Responses are typically JSON. Click REST strengths. It is simple, widely understood, and HTTP responses are inherently catchable. But it has real weaknesses. Overfetching. You get back more data than you needed. Underfetching. You have to make multiple requests to different endpoints to assemble the full picture a client needs. ClickGraphQL was designed specifically to solve those REST problems. The client sends a single query that precisely specifies which fields it needs across which entities, and the server returns exactly that. Nothing more, nothing less. Single endpoint, strongly typed schema, no over or underfetching. The downsides. Caching becomes more complex since everything goes through one endpoint, and the famous N+1 query problem can arise if resolvers are not carefully written. ClickGRPC is Google's remote procedure call framework, built on protocol buffers in HTTP/2. You define your service contract in a .proto file, as you see in the code on screen, and protobuf generates client and server code in any language. ClickGRPC is 5 to 10 times faster than JSON REST for equivalent operations, because the binary protobuf encoding is much more compact and efficient than text JSON. It supports bidirectional streaming natively, and strongly typed contracts mean you catch mismatches at compile time, not in production. The downsides. Proto files are binary, and not human-readable. Browser support is limited without a gRPC web proxy. Click the Practical Selection Guide. Use REST for public-facing APIs and simple CRUD services, where simplicity and catchability matter. GraphQL for flexible front-end-driven queries, where the client needs fine control over data fetching. gRPC for internal service-to-service calls where performance is paramount. Not every service interaction needs to be synchronous. In fact, for many workloads, asynchronous communication is the right model. A message queue is a classic async, point-to-point delivery mechanism. A producer sends a message to a queue. A consumer reads that message, processes it, and sends an acknowledgement, ACK. Once acknowledged, the message is deleted from the queue. One message, one consumer. An event stream is fundamentally different. It is a durable, ordered log. Events are written and retained permanently. Multiple independent consumers can read the same event at their own pace, independently. You can replay from any point in history. Click Why do we invest in this complexity? 4 reasons. Decoupling. The producer and consumer don't need to be running at the same time. The email service doesn't need to be up when the order service places an order. Buffering. If you get a traffic spike, the queue absorbs it. Consumers process at their own pace. Your database doesn't get hammered by a burst of simultaneous writes. Fan-out. One event can be consumed by many independent services, each doing something different with it. Retry. If a consumer fails, it hasn't lost the message. It can retry without the producer ever knowing. Click the key products, RabbitMQ for traditional task queues and request reply patterns, Apache Kafka for high-throughput event streaming, event sourcing, Audit logs. A WSSQS for managed queues in AWS ecosystems. A WSSNS for fan-out pub/sub, one message to many subscribers. Redis streams for lightweight streaming without the Kafka overhead. Click the diagram contrasts the two models side by side. In the queue on the left, the order service publishes a message, and one email worker processes it. In the Kafka stream on the right, the payment service produces an event that is independently consumed by an analytics service, a fraud detection service, and a notification service, all from the same durable topic. Next, what about real-time communication? Chat messages, live scores, collaborative editing, trading tickers. These need the server to push data to the client as events happen. Standard HTTP request response doesn't work for this, because it is the client that initiates every request. Let us look at the three patterns, in order of increasing capability. Click short polling. The client just asks the server, is there anything new? Every n seconds. Extremely simple to implement, but deeply wasteful. Most responses are empty, and you always have latency equal to your polling interval. Click long polling. The client sends a request, and the server holds it open without responding until data is available, or a timeout occurs. When the server has something to send, it responds, and the client immediately opens a new request. Lower latency than polling, but still half duplex. You need a new HTTP request for every response. At large scale, holding thousands of open connections on your servers is expensive. Click WebSockets, the upgrade. The client sends a standard HTTP request with an upgrade WebSocket header. The server responds with 101 switching protocols. From that point on, the connection is no longer HTTP. It is a raw bidirectional TCP channel. Either side can send data at any time, independently. Sub-millisecond latency, full duplex. The trade-offs. WebSocket connections are stateful. If you have multiple servers, a client connected to server 1 cannot receive pushes from server 2. You need sticky routing, or a message broker between servers. Server-sent events is a lighter alternative, unidirectional server push over a regular HTTP connection. Great for dashboards and notification feeds, where you never need the client to send data on this channel. Next. Now let us zoom out to architectural patterns, the high-level strategies for how you organize services, data flows, and your overall system topology. One of the most debated topics in modern software architecture. Should you build a monolith or microservices? A monolith packages all functionality into a single deployable unit. User accounts, orders, payments, inventory, all in one codebase, one deployment, one database. Click monolith advantages that are genuinely underrated. Development is simple. You run one thing. Deployments take one command. Testing is straightforward. Everything is in one process. Transactions across modules are easy, because you are just calling in-process functions. Most startups and early-stage products should start with a monolith. The limitations. It scales as a unit. If your payment processing is the bottleneck, you have to scale the entire monolith even though only that module is under pressure. At scale, build times get long, the deployment frequency slows, and technologies in different modules can become constraints. Click microservices decompose the system into independently deployable services, each owning its own data store. No shared database. You get independent scaling. Scale just the service that is under load. Technology heterogeneity. The recommendation engine can be Python. The payment service can be Java. The chat service can be Go. Fault isolation. If the recommendation service crashes, checkout still works. But the costs are real. You now have a distributed system, with all its inherent complexity. Network calls between services fail and have latency. Distributed transactions require coordination protocols. Data consistency is harder without a shared database. Click the diagram shows it clearly. Left side, one box, one database. Simple. Right side, an API gateway routing to 4 services, each with its own database. Powerful, but complex. The practical advice. Start with a well-structured monolith. Extract to services when you have a clear scaling problem or team autonomy requirement, not as a default architectural choice. Next. In a microservices architecture, you need 2 distinct infrastructure layers to manage communication. The API gateway is the single entry point for all external client traffic. Every request from a mobile app or browser hits the gateway first. Click what does the gateway do? It handles authentication and authorization. It validates JWT tokens before a request ever reaches your services. Rate limiting. It throttles abusive clients at the edge. Request routing. It dispatches requests to the correct downstream service based on the URL path. SSL termination. It handles TLS, so your internal services communicate in plaintext behind the firewalled internal network. Request transformation. It can translate between REST and gRPC, or add remove headers. And circuit breaking. It can stop forwarding requests to a service that is currently failing. Click the service mesh is different. It handles service-to-service communication within your cluster. Instead of baking network logic into your application code, a sidecar proxy is deployed alongside every service container. Envoy Proxy is the most common sidecar. The sidecar handles MTLS, mutual TLS, so all service-to-service communication is encrypted and mutually authenticated. It provides automatic retry logic, timeout enforcement, load balancing across service instances, and distributed tracing, all without a single line of application code change. Click the diagram shows both layers. External clients go through the gateway. Inside the cluster, each service has its sidecar proxy, forming the mesh. A central control plane, Istio or Linkerd, distributes policy configuration to all sidecars. The services themselves just talk to their local sidecar, and the mesh handles everything else. Next, event-driven architecture, or EDA, is a style where services communicate by publishing and consuming events, rather than making direct synchronous API calls. Instead of the order service calling the email service, the inventory service, and the shipping service in sequence, it publishes one event, order placed. Each downstream service independently subscribes and reacts to that event in its own time. There are 3 subpatterns within EDA. Event notification. A service broadcasts that something happened. Consumers decide what to do. Simple, and maximally loosely coupled. Event carried state transfer. The event itself contains all the data consumers need. Consumer ID, order total, items. So downstream services don't have to call the producer back to get more information. Event sourcing. Instead of storing the current state of an entity, you store the history of all events that brought it to its current state. The event log is the source of truth. You can replay the log to reconstruct state at any point in time, invaluable for auditing and debugging. CQRS, Command Query Responsibility Segregation, is frequently paired with event sourcing. The write model handles commands and emits events. The read model subscribes to those events and builds optimized query-friendly views. Your read view in a key value store, your write model in an event store, completely separate, each optimized for its purpose. The diagram shows a complete EDA flow. The customer places an order, a command. The order service emits an order-placed event to Kafka. Independently, the email service, inventory service, and shipping service all consume that same event and take their own actions. The read model also consumes events to keep a current view for queries. Next, imagine a downstream service is failing, responding with errors or timing out. If your system keeps sending requests to it, what happens? Your threads pile up waiting for responses that never come. Your connection pools exhaust. The failure cascades upward. A database timeout in one service becomes an outage across your entire platform. This is the cascade failure problem, and it is one of the most dangerous failure modes in distributed systems. The circuit breaker pattern prevents this. It monitors calls to a downstream service and stops making them when the failure rate exceeds a threshold. 3 states. Closed is normal operation. Request pass through. Failures are tracked in a rolling window. When the failure count exceeds your configured threshold, say 50% error rate over the last 10 seconds, the breaker trips to open. Open means the breaker is tripped. All requests to the failing service are instantly rejected with a fast failure. No network call is made. Your threads are freed immediately. The client gets a cached result or a graceful error message. After a configured timeout, say 30 seconds, the breaker transitions to half open. Half open. Let one probe request through. If it succeeds, the circuit closes and normal traffic resumes. If it fails, back to open for another timeout. Libraries available. Netflix Hystrix for Java, Resilience 4J as its modern replacement, Python Circuit Breaker Library, and Istio can enforce circuit breaking at the service mesh level. No code changes required. Related patterns you should know alongside the circuit breaker. Retry with exponential backoff and jitter. Don't hammer a recovering service with a thundering herd of retries. Timeout. Always set explicit deadlines on network calls. Never wait indefinitely. Bulkhead. Isolate your thread pools per downstream dependency, so one slow service can't exhaust all your threads. Next, let us move into storage, the long-term home for your data. Choosing the right kind of storage for the right kind of data is a core system design skill. The first rule of large file storage: do not put files in your relational database. Images, videos, documents, backups, log archives. These belong in object storage. A relational database is optimized for structured, transactional data. It is terrible at storing gigabytes of binary blobs. Object storage is built specifically for this. Object storage has a flat namespace, no directories, just a bucket and an object key. Each object is a bundle of data plus metadata, accessed via simple HTTP operations: get, put, delete. And it scales to essentially infinite capacity, durably storing data across multiple availability zones. The characteristics you care about in practice. Flat namespace with hierarchical key naming convention like user/42/avatar.jpg. HTTP-based access, no special drivers. Infinitely scalable. Built-in versioning. Lifecycle policies to auto-archive old objects to cheaper storage tiers, and cross-region replication. Click the Smart Upload pattern using pre-signed URLs. Never route file uploads through your application servers. They become a bottleneck immediately. Here is the correct pattern. The client asks your application server for an upload URL. Your server asks S3 to generate a pre-signed URL, a time-limited URL that gives upload permission for a specific object key. Your server returns that pre-signed URL to the client. The client uploads the file directly to S3, completely bypassing your application servers. S3 then fires an object-created event that triggers your processing pipeline, resizing images, transcoding video, virus scanning. Click Major Providers: AWS S3, Google Cloud Storage, Azure Blob Storage, MinIO if you need a self-hosted S3 compatible solution. Next, how does full-text search work at scale? You cannot use like %search_term% in a SQL query that does a full table scan on every search. At millions of documents, it is completely unusable. Search engines solve this with an inverted index. Click Here is the concept. Instead of storing documents and scanning them for search terms, you build a reverse mapping. For each word, store the list of documents that contain it. The table on screen shows the idea. The term Python appears in documents 1, 3, and 7. The term pattern appears in documents 3 and 5. A search for Python and pattern is just set intersection. Documents containing both terms is just document 3. This is blazing fast. Constant time lookups in the index, not linear scans of documents. Click TF-IDF is the classic relevance ranking algorithm. For a given term and document, the score is the product of two factors. TF term frequency. How often does this term appear in this specific document? Documents that mention the word more are probably more relevant. IDF, inverse document frequency. How rare is this term across all documents? A term that appears in every document like the gives you no useful signal. A rare term like quorum is much more indicative of the document's topic. The log of n over n sub t penalizes common terms and rewards rare ones. Click the diagram shows Elasticsearch's architecture. Documents go through an analysis pipeline, tokenization, normalization, stemming, and are stored in shards across the cluster. A coordinator node receives incoming search queries and fans them out to the relevant shards in parallel. Results come back, are merged and ranked, and returned to the application. Products, Elasticsearch and Apache Solr, are the mature self-hosted options. TypeSense and Mealysearch are modern, developer-friendly alternatives. Algolia is the SaaS option. Next, a specific class of data that deserves its own database type: time series data. Any data where time is the primary dimension. Infrastructure metrics, application performance metrics, IoT sensor readings, financial price ticks. Why can't you just use PostgreSQL? Because time series workloads are completely unlike typical transactional workloads. Writes are always appends. You never update old data points, you only add new ones. Queries are almost always time range aggregations. Give me the average CPU utilization over the last hour, grouped into 5-minute buckets. Data volumes are enormous, thousands to millions of data points per second from large fleets. Click Purpose-built time series databases are optimized for exactly this workload. They use columnar storage that compresses repeated timestamps and sensor IDs extremely efficiently. Automatic time-based partitioning, data for each time interval goes into its own chunk, making range queries fast and making it easy to drop old data. Automatic downsampling, compress old high-resolution data into lower-resolution summaries automatically. And built-in aggregation functions that are much simpler to use than equivalent SQL. Click Common Products, InfluxDB for application metrics, and IoT. Prometheus is the de facto standard for scraping metrics from infrastructure and Kubernetes workloads. TimescaleDB extends Postgres with time series capabilities. You keep your SQL tooling. Click House for extreme scale real-time analytics. Click the diagram shows a typical Prometheus plus Grafana observability stack. Services expose metrics on an HTTP endpoint. Prometheus scrapes them on a schedule. The data goes into the time series database. Grafana queries it to build dashboards. And Alert Manager fires alerts to PagerDuty or Slack when metrics breach thresholds. Next, we have covered infrastructure and communication. Now, reliability and security. How do you build systems that stay up, stay correct, and stay safe? Availability is the fraction of time your system successfully serves requests. The formula is MTTF divided by MTTF plus MTTR, mean time to failure, divided by the sum of that, and mean time to recovery. To maximize availability, you want either fewer failures, higher MTTF, or faster recovery, lower MTTR. Both matter. Click the famous nines table. This is worth memorizing. 2 nines 99% sounds high, but that is 3.65 days of downtime per year. Most consumer products target higher. 3 nines 99.9% is 8.7 hours per year. This is a reasonable baseline for internal tools. 4 nines, 99.99%, is only 52 minutes per year. This is what most customer-facing services target. 5 nines, 99.999%, is 5.2 minutes per year. This is typically only required for critical infrastructure, payments, telephony, hospitals. Notice how each additional 9 is approximately 10 times harder and more expensive to achieve. Click techniques for achieving high availability, redundancy at every layer. No single point of failure. 2 load balancers. 3 database replicas. Multiple availability zones. If any one thing failing causes an outage, you do not have high availability. Graceful degradation. When a dependency fails, degrade gracefully. Return cached results. Hide the broken feature. Do not cascade the failure to the entire system. Chaos engineering. Intentionally inject failures into production to find weaknesses before they find you. Netflix's Chaos Monkey is the famous example. SLIs, SLOs, and SLAs, service level indicators, are what you measure. Service level objectives are the targets you set internally. Service level agreements are the contracts you make with customers. Click the diagram shows a multi-AZ deployment, 2 separate availability zones, each with its own application server and database. A load balancer routes traffic to both zones. The primary database in AZA replicates synchronously to the replica in AZB. If the entire AZA fails, AZB can take over with minimal downtime. Click I will leave you with a quote from Werner Vogels, the CTO of Amazon. Everything fails all the time. It sounds grim, but it is the right mental model. Assume every component will fail. Design your system to detect it, tolerate it, and recover from it automatically without human intervention. Rate limiting is the mechanism by which you control how many requests a given client can make in a time window. It protects you from malicious abuse, from DOS attacks, and from accidental bugs in clients that send runaway traffic. Click 4 common algorithms. Token bucket. Imagine a bucket that holds up to n tokens. Tokens are added at a fixed refill rate, say 10 per second. Each incoming request consumes 1 token. If the bucket is empty, the request is rejected. This allows natural bursts up to the bucket capacity. Great for bursty traffic patterns. Leaky bucket. Requests go into a queue and are processed at a constant, fixed rate, like water leaking from a bucket. Whatever bursts happen on the input side, the output is always smooth. Good for rate shaping, keeping downstream services from being overwhelmed. Sliding window log. Track the exact timestamp of every request in a rolling window. Accurate, but memory intensive. You are storing potentially many timestamps per user. Sliding window counter. Combine 2 fixed window counts with interpolation to approximate a sliding window. Much more memory efficient, with only minor accuracy trade-offs. This is what most production implementations use. Click the implementation. For each unique client, keyed by user ID and endpoint, store a token count and last refill timestamp in Redis. Use a Lua script to atomically check and decrement the token count. Redis runs Lua scripts as a single atomic operation. No race conditions, no locks needed. Click the diagram shows the full flow. Client requests hit the API gateway, which calls the rate limiter. The rate limiter checks and updates state in Redis. Requests under the limit are forwarded to the application. Requests over the limit get a 429 too many requests response immediately, with a retry after header telling the client how long to wait. 2 concepts that are often confused. Authentication is who are you, verifying identity. Authorization is what are you allowed to do, checking permissions. Authentication happens first, always. Click session-based auth is the traditional stateful approach. User submits credentials, server validates them, creates a session record in Redis, and returns a session ID cookie. Every subsequent request from that client includes the cookie, and the server looks up the session in Redis to verify identity. Simple and straightforward. The downside. Every request requires a Redis lookup, and when you scale horizontally, all your servers must share access to the same session store. If Redis goes down, all sessions are lost. Click JWT Auth, JSON Web Tokens, is the stateless alternative. User submits credentials, server validates them, and creates a signed token, a base 64 encoded JSON payload, containing user ID, roles, and expiry, cryptographically signed with the server's secret key. The client stores this token, and sends it in the authorization header on every request. Here is the key insight. Any server can verify a JWT signature without a database lookup. Just check the signature against the secret key, and check the expiry claim. This scales horizontally with zero coordination between servers. The caveat. If you need to revoke a JWT before it expires, say, because a user logs out or their account is compromised, you need a token block list in Redis, which is a form of state, partially recreating the session problem. Click the sequence diagram shows the full JWT login and refresh flow. User logs in, gets an access token valid for 15 minutes, and a refresh token valid for 7 days. Every API call includes the access token in the authorization header. The gateway verifies the signature locally. When the access token expires, the client uses the refresh token to silently obtain a new access token without forcing the user to log in again. You can build the best system in the world, but if you cannot see what is happening inside it, you are flying blind. Observability is the discipline of making your system's internal state understandable from its external behavior. There are 3 pillars of observability. Click metrics. Numeric measurements aggregated over time. HTTP_requests_total. P99_latency_ms. CPU_utilization. Error_rate. Metrics are cheap to store and fast to query. They tell you that something is wrong. Tools. Prometheus, Datadog, CloudWatch. Click logs. Timestamped, structured records of individual events. Each log entry should be structured JSON, not free-form text string, with fields like timestamp, log level, service name, trace ID, message, and relevant context. Logs tell you what happened. Tools. The ELK stack, Elasticsearch, Logstash, Kibana, Loki, and Splunk. Click traces. If metrics tell you something is slow, and logs tell you what happened, traces tell you where the time went. A trace follows a single user request through every service it touches. It is represented as a tree of spans, 1 span per service hop, each recording the service name, operation, start and end time, and status. The Gantt chart on screen shows a real trace. A total request takes 90 milliseconds. The API gateway spends 15 milliseconds on auth and 5 on routing. The user service spends 25 milliseconds on a database query. The order service and inventory service run in parallel. Note the overlapping spans. Without distributed tracing, you would never know that. Click OpenTelemetry is the emerging open standard for instrumentation. A single SDK works across languages, automatically propagates trace context via HTTP and gRPC headers, and exports to any compatible tracing backend. Next. Now for the part you have been waiting for. Case studies. Let us apply everything we have learned to real system design problems, the exact type of questions asked at top-tier engineering interviews. Classic first system design problem. Build a URL shortener like bit.ly. The requirements. Users submit a long URL and get a short URL like show, rt/ab3xyz back. Anyone who visits the short URL gets redirected to the original long URL. 100 million URLs created per day, with a 10:1 read-to-write ratio, meaning 1 billion redirects per day. Click estimations. Writes. 100 million divided by 86,400 seconds is roughly 1,160 write requests per second. Reads. 11,600 per second. Storage. 100 million URLs times 500 bytes per URL record times 365 days times 5 years is about 91 terabytes. These numbers immediately tell you what problems you need to solve. Read scaling, storage at scale, and fast redirects. Click the critical design question. How do you generate short codes? You need globally unique 7-character codes. Using all alphanumeric characters, 62 options per character, gives you 62 to the 7th power, roughly 3.5 trillion combinations. More than enough. 3 options. Hash the long URL with MD5 or SHA-256 and take the first 7 characters. Simple but creates collision risk. Generate a distributed numeric ID using a Snowflake generator and base 62. Encode it. This is the best approach. Or pre-generate a pool of random codes and hand them out from a queue. The recommended approach is base 62, encoding a Snowflake ID. Those IDs are globally unique, time-ordered, and extremely high throughput. Click the architecture on the right. Write path. Client posts to the API gateway, which rate limits and routes to the write service. The write service gets a Snowflake ID, stores the mapping in MySQL short to long URL, and populates a Redis cache. Read path. Get request for a short code checks Redis first. Cache hit returns the redirect immediately. Cache miss queries MySQL and populates the cache. The read-to-write ratio of 10:1 means your Redis cache will absorb the vast majority of traffic. Most short URLs, once shared, get many more reads than writes. Your MySQL is mostly for durability and cache misses on cold entries. Next. Design a distributed key-value store. Essentially, design a simplified version of Cassandra or DynamoDB. Put a key-value pair, get it back, survive node failures, and persist data across restarts. Click the 4 core design decisions. Partitioning. Use consistent hashing to distribute keys across nodes. When nodes join or leave, minimal keys need to move. Replication. Replicate each key to n nodes, typically 3. This tolerates up to n-1 node failures without data loss. Use quorum reads and writes. If n is 3, r is 2, and w is 2, then r plus w equals 4, which is greater than n equals 3. This quorum condition guarantees that any read will see the most recent written value. Write path inside a node. This is the LSM tree data structure. A write appends to the write-ahead log on disk. This ensures durability, so the write survives a crash. Then the write goes into the mem table in memory, an in-memory sorted key value map. Fast. When the mem table reaches its size limit, it is flushed to disk as an immutable SS table, a sorted string table. Background compaction processes merge SS tables, eliminating duplicate or deleted keys. Read path. Check the mem table first. Fastest. No disk I/O. Then use a Bloom filter to check whether the key might be in each SS table before doing an expensive disk read. Bloom filters have 0 false negatives. If the filter says the key is not in an SS table, it is definitely not there. Only read the SS tables that might contain the key, newest to oldest. Click. This LSM tree architecture is exactly how Apache Cassandra, RocksDB, LevelDB, and Azure Cosmos DB store data internally. Next, design a system that delivers push notifications, emails, and SMS messages to millions of users per day. Requirements: multiple delivery channels, millions of daily notifications, pluggable providers for each channel, and reliable retry on failures. Click the flow. A service or internal event triggers a notification request. The notification service validates it, checks the user's preferences. Are they opted out? Is it during their quiet hours? What contact information do they have? Then routes to the appropriate channel queues. Each channel has its own queue. Workers pull from the queues and call the third-party providers, Google's FCM and Apple's APNs for push notifications, SendGrid for email, Twilio for SMS. If a delivery attempt fails, the message is re-queued with exponential backoff for retry. Click Key Design Choices. Per channel queues, a slow SMS provider or high SMS volume should never delay email delivery. Independent queues mean independent scaling and independent failure domains. The user preferences database stores opt-out status, notification frequency caps, quiet hours, and verified contact information. Without this, you risk spamming users and triggering compliance violations. A notification log records every delivery attempt, used for deduplication, ID impotency, and delivery receipt tracking. If a retry fires twice due to a bug, the deduplication check prevents the user from receiving the same notification twice. Click the diagram shows the complete flow. Trigger events arrive at the notification service. It checks preferences, splits the load into per-channel queues. Workers pick them up and call the external providers. Failed deliveries loop back into the queues. Next, we covered rate limiting as a concept earlier. Now let us design it as a proper distributed service. The requirements: per user and per IP limits, enforced consistently across an entire fleet of API servers, returning 429 with a retry after header when limits are exceeded. Click the distributed challenge. Naive in-memory counters per server fail as soon as you have multiple servers. A client could send 10 requests, each to a different server, and each server sees only one, far below any per-server limit. The solution: centralized, atomic state in Redis. The Lua script on screen is the heart of the implementation. It reads the current token count and last refill timestamp for the given key. It calculates how many tokens have been added since the last refill. It recaps at the maximum capacity. If there is at least one token available, it decrements, saves, and returns, allowed. Otherwise rejected. Critically, the entire Lua script runs atomically. Redis executes it as a single indivisible operation. No race conditions, no distributed locks needed. Click the architecture. Clients hit the API gateway, which calls out to the Redis cluster for every request. The Redis cluster stores token bucket state, keyed by user_ID:endpoint. The gateway gets back allow or deny and acts accordingly. A Redis replica provides high availability for the rate limiter state itself. Design a chat system at scale, one-to-one and group messaging, real-time delivery when online, offline storage and delivery, 30-day message history, and 50 million daily active users sending 40 messages each per day. That is 23,000 messages per second. Click the key architectural decisions. Connection layer. Use WebSockets. Persistent, bidirectional, low latency. Each WebSocket server holds approximately 100,000 concurrent connections. A connection registry in Redis maps user_ID to the server ID they are currently connected to. This registry is what enables cross-server message routing. Message flow for one-to-one chat. Alice sends a message via her WebSocket to chat server 1. Server 1 immediately persists the message to Cassandra. Wide column, designed for high write throughput and efficient time range reads, ideal for chat history. Server 1 then queries the connection registry. It gets back Bob is on server 2. Server 1 routes the message to server 2 via an internal message bus. Server 2 pushes the message down Bob's WebSocket connection. Bob receives it in milliseconds. Offline delivery. If Carol is not connected, her message goes into an offline message queue. When Carol reconnects, the server delivers all pending messages in order, before resuming real-time messages. Group chat. Fan out. When a message goes to a group with 1,000 members, you need to deliver to up to 1,000 WebSocket connections, potentially across many servers. At scale, do this fan out via Kafka topics, to decouple the write speed from the fan out speed. Click message storage. Cassandra is the right choice here. It is write optimized, handles high throughput easily, and its data model naturally supports time-ordered message retrieval per conversation. Partition by conversation ID, cluster by timestamp. Next, design a YouTube-scale video streaming service. Upload raw videos, transcode them into multiple resolutions, and serve them to 100 million daily users, with adaptive bitrate streaming and global low latency. Click the upload and processing pipeline. Creators upload raw video directly to object storage via a pre-signed URL, just like we discussed. Object storage fires an object-created event, which enqueues a transcoding job in a message queue. Multiple transcoding workers pick up the job in parallel. One encodes 360p and 720p. Another encodes 1080p and 4K simultaneously. The transcoded video is segmented into small HLS chunks, typically 2 to 10 seconds each, and stored in a CDN-connected object store. Metadata goes into Postgres. Click streaming. The key technology is HLS, HTTP live streaming. Each video is broken into small segments, plus a manifest file called an .m3u8 file that lists all the segment URLs across all available quality levels. When a viewer clicks play, the player fetches the manifest. It then uses an adaptive bitrate algorithm, ABR, to select the highest quality it can sustain, given the viewer's current bandwidth and buffer state. If bandwidth drops, it steps down to a lower quality. If bandwidth improves, it steps up. The viewer always gets the best possible quality without buffering. All segments are served from CDN edge nodes closest to the viewer, not from your origin servers. Your origin only ever transcodes once. The CDN handles delivery to tens of millions of concurrent viewers. This architecture, object storage for raw assets, async transcoding pipeline, CDN for delivery, is fundamentally how YouTube, Netflix, Twitch, and every other major video platform operates. Next, design a web crawler that indexes the entire public web. 1 billion pages, recrawled every 4 weeks, with politeness policies and duplicate detection. Click the 6 core components. Seed URLs, your starting set, major sites like Wikipedia, Reddit, news outlets. The crawler bootstraps from here and discovers the rest of the web by following links. URL frontier, a priority queue of URLs waiting to be crawled. URLs are prioritized by factors like PageRank, domain authority, and freshness. How recently the content likely changed. DNS cache, resolve each domain's IP address once per crawl and cache it aggressively. DNS lookups are expensive at this scale. Fetch workers, a distributed pool of workers that obey robots.txt, which tells crawlers which paths they are not allowed to access, and respect crawl delay directives. Being polite is ethically important, and practically necessary to avoid getting IP blocked. Content parser and link extractor, parse the downloaded HTML, extract all links, and add new, unseen ones to the frontier. Also extract the text content for indexing. Duplicate detection, 2 levels. First, URL deduplication with a Bloom filter, extremely memory efficient for answering, "Have we seen this URL before?" Second, near duplicate content detection with SymHash. Different URLs can have identical or nearly identical content. We should store each page only once. Click the flow diagram shows how these components connect. Seeds feed the frontier. Workers fetch pages and parse them. Extracted links go through Bloom filter deduplication before requeuing. Extracted content goes through SymHash deduplication before being stored in the object store and indexed. Next, for our final section, we go deeper: distributed consensus, globally unique ID generation, large-scale data pipelines, and probabilistic data structures. One of the fundamental problems in distributed systems. How do multiple nodes agree on a single value when nodes can fail and the network can partition? This is the consensus problem. Without it, your distributed database can have 2 nodes that disagree about the current value of the same key, which is a correctness disaster. Raft is the dominant consensus algorithm in production systems today. It was designed explicitly to be more understandable than the previous standard, Paxos. Click every node in a Raft cluster plays one of 3 roles: follower, passive, responds to requests from a leader. If it stops receiving heartbeats, it assumes the leader is dead and transitions to candidate. Candidate. The node believes there is no leader. It increments the current term number, votes for itself, and sends request vote RPCs to all other nodes. The first node to collect votes from a majority becomes the leader. Leader, the sole authority for all rights. The leader sends periodic heartbeat messages via append-entries RPCs to all followers, which also carry log replication payloads. If the leader stops sending heartbeats because it crashed, followers time out, and a new election begins. Log replication. When a client writes to the system, the leader writes the entry to its local log, then sends it to all followers in parallel. The entry is committed, made permanent, and applied to the state machine as soon as the leader receives acknowledgments from a majority of nodes. Even if some followers are down, as long as a majority are up, the system makes progress. Click the Raft guarantee. A committed entry will not be lost, even if minority nodes fail. A leader will never overwrite committed entries. The system remains available as long as more than half the nodes are healthy. Raft is the consensus algorithm powering etcd, which is the distributed store at the heart of Kubernetes. Also CockroachDB, Consul TIKV, and InfluxDB2. Next. In a distributed system, how do you generate IDs? You cannot use auto_increment on a single database. That database is a bottleneck and a single point of failure. You need a strategy that is globally unique, time-sortable, high throughput, and fits in a standard 64-bit integer. Click Twitter Snowflake is the widely adopted solution. A 64-bit integer is partitioned into 3 fields. The first 41 bits store a millisecond precision timestamp relative to a custom epoch. 41 bits gives you 69 years of IDs. The next 10 bits identify the node generating the ID, supporting up to 1024 nodes. The final 12 bits are a per millisecond sequence number, up to 4096 IDs per millisecond per node. The total throughput per node, 4096 IDs per millisecond, which is about 4 million per second. Across 1024 nodes, the total system capacity is 4 billion IDs per second, far more than any realistic workload. And crucially, since the timestamp is the high bits, Snowflake IDs are naturally sorted by creation time. You can sort them as integers and get temporal ordering for free. This is invaluable for pagination. Click Alternatives. UUID v4 is simple and requires no coordination whatsoever, but it is 128-bit and has no temporal ordering. You cannot paginate using UUIDs. ULID, Universally Unique Lexicographically Sortable Identifier, is a time-sortable UUID variant, but has less ecosystem adoption. MongoDB Object ID is 96-bit with a timestamp prefix. DB Auto Increment is the baseline, simple, but a SPOF. Click the Python implementation on the right, is a thread-safe Snowflake generator. It uses a threading lock to prevent race conditions between threads on the same process, carefully handles the case where the sequence number wraps around within the same millisecond, and bit shifts the 3 components into their correct positions in the 64-bit ID. Next. Large-scale data systems need 2 conflicting properties. They need accuracy, processing all historical data correctly, and low latency, showing near real-time results. No single system handles both perfectly. The Lambda architecture addresses this by running 2 parallel processing pipelines. Click the batch layer processes the complete historical dataset periodically, perhaps once per hour or once per day. It is slow but perfectly accurate, because it reprocesses everything. Apache Spark and BigQuery live here. The results are complete but potentially hours old. The speed layer processes only data from the last few minutes or hours in real time. It is fast but may be slightly inaccurate because of the complexities of real-time processing. Flink and Kafka Streams live here. It fills the freshness gap left by the batch layer. The serving layer merges results from both the accurate batch views for older data and the recent speed views for the last period not yet covered by the batch run. Queries hit this layer. Click Kappa architecture is the modern simplification. Remove the batch layer entirely. A single streaming system, usually Kafka plus Flink, handles everything. To rebuild historical views, you replay the full event history through the streaming pipeline. This is simpler to operate, but requires your streaming infrastructure to handle high replay throughput. As streaming technology has matured, Kappa has become increasingly popular for new systems. Lambda remains in heavy use in the enterprise where Spark pipelines are already established. The final data structure we need in your system design toolkit, the Bloom filter. A Bloom filter is a probabilistic data structure that answers one question with remarkable efficiency. Is this element definitely not in the set, or is it possibly in the set? 2 key properties. False negative rate, 0. If a Bloom filter says an element is not present, it is guaranteed to not be present. False positive rate, configurable. If it says an element is present, there is a small probability epsilon that it is wrong. You tune epsilon by choosing the size of the bit array and the number of hash functions. Space requirement, approximately 10 bits per element for a 1% false positive rate. Compare that to a hash set storing the actual values, orders of magnitude smaller. Click how it works. A Bloom filter is just a bit array of m bits, all initialized to 0, and k independent hash functions. To add an element, hash it with all k functions. Set those k-bit positions to 1. To check if an element is present, hash it with the same k functions. If any of those bit positions is 0, the element is definitely not in the set. You can return a definitive NO immediately. If all bits are 1, it is probably present, but could be a false positive due to bit collisions from other elements. Click Real System Design Applications. A web crawler uses a Bloom filter as its Seen URLs set. Before putting a URL in the frontier queue, check the Bloom filter. If it says definitely not seen, add to the queue. If it says probably seen, skip it. The memory required to track a billion URLs this way is tiny compared to storing them all. Cassandra and RocksDB use Bloom filters at the SS table level. Before doing an expensive disk read, to check if a key exists in an SS table, check the Bloom filter. If the key is definitely not there, skip the disk read entirely. This enormously reduces read amplification. Cache penetration protection. Before a cache miss triggers a database query, check a Bloom filter of known existing keys. Requests for genuinely non-existent keys, like scraper attacks. Let us now talk about how to actually perform in a system design interview. The content we have covered is the knowledge. This is the methodology. A strong system design interview follows a clear structure in roughly 45 minutes. Click Step 1. Clarify requirements, 5 minutes. Ask questions. Never start designing. What are the core use cases? Is this read-heavy or write-heavy? How many users? What QPS? How much data? Consistency or availability? Which takes priority for this domain? Any existing systems to integrate with? You will show the interviewer immediately that you think before you act. Click Step 2. Estimate scale, 3 minutes. Back of the envelope. Derive the requests per second, both read and write. Determine your storage requirements over 5 years. Calculate peak bandwidth. These numbers will drive every subsequent design decision. Click Step 3. High-level design, 10 minutes. Draw the boxes. Clients, API gateway, services, databases, caches, queues, CDN. Walk through the data flow for the 1 or 2 primary use cases. Make sure your interviewer agrees with the overall structure before you dive deep. Click Step 4. Deep dive, 15 to 20 minutes. Pick 2 or 3 specific areas and go deep. The interviewer will often guide you. Common deep dive areas: database schema design, caching strategy and invalidation, failure handling, consistency trade-offs. Click Step 5. Identify bottlenecks and scale, 5 minutes. Do not wait for your interviewer to poke holes. Find them yourself. What is the single point of failure? What is the hot shard? What breaks first at 10x load? Then propose solutions. This last step often separates good candidates from great ones. Click the key meta-skill threading through all of this. Articulating trade-offs. There is no single right answer in system design. For every choice you make, there is a cost. The engineer who says, I chose this because X and Y, and the trade-off is Z and W, will always outperform the engineer who says, this is the right answer. Show your thinking, not just your conclusion. Let us bring it all together. Click the most important meta lesson. There is no single right answer in system design. Every architectural decision is a trade-off. SQL versus NoSQL, sync versus async, monolith versus microservices, consistency versus availability. What makes a great system designer is not knowing the correct answer. It is being able to clearly articulate what you gain and what you give up with each choice, and making decisions that fit your specific constraints. Click Here is your toolkit summary. To scale reads, add caching with Redis. Add read replicas to your database. Put a CDN in front of your static content. To scale writes, shard your database. Move work to async queues. Apply CQRS to separate your write and read models. To decouple services, introduce message queues and event streaming. Services should not depend on each other being up. To ensure high availability, eliminate all single points of failure. Deploy multi-AZ. Implement circuit breakers. To guarantee consistency, use Raft consensus for distributed agreement. Use distributed transactions only when necessary, and understand when eventual consistency is actually acceptable for your use case. Click Memorize these numbers. Same data center network round trip, half a millisecond. SSD random read, 100 microseconds. RAM access, 100 nanoseconds. HTTP request overhead, about a millisecond. Redis operation, around 0.1 milliseconds. These numbers let you do back-of-the-envelope latency estimates in your head during an interview. Click the diagram on the right shows the 6 pillars every system should be evaluated against: scalability, high availability, performance, durability, consistency, and observability. These are not checkboxes. They are tensions you balance continuously. Click I will leave you with Kent Beck's famous principle. Asterisk. Make it work. Make it right. Make it fast. Design for today's actual scale. Build in the hooks for tomorrow's growth. But do not over-engineer. Complexity is always a cost, and you pay it every day in bugs, onboarding time, and operational burden. Thank you for watching. If this was helpful, like and subscribe. There is a lot more coming in this series. Links to the GitHub slides are in the description. See you in the next one.